For this example, we're given a function which is written as a power series where the coefficients kind of alternate between 1s and 2s. So it's 1 plus 2x plus x squared plus 2x cubed plus x to the fourth, etc. And we are asked to find the radius of convergence and the interval of convergence of this power series. We're also asked, if possible, to try to find a formula for this power series in a form that is not a power series itself. But when we do that, we have to be very careful about making sure that the interval of convergence matches our formula, if we're able to do it. And I would actually like to start there. So the first thing I would like to do is break up this power series into a sum of two different power series, one of which just has the coefficients that are 1s and the other one that has the 2 coefficients. So I'll just write this out like follows, or as follows: 1 plus x squared plus x to the fourth, etc. There's the even part, plus 2 times, factor out the 2 and what's left, x plus x cubed plus x to the fifth, etc. And what we notice that is that if this 2 weren't here, we could add all of this together and we would have a nice geometric series. So I said if this 2 wasn't here, but another option is what if there is a 2, but the 2 is out here, right? And so if we double this, we can combine all this into a nice geometric series. But then what we have to do is make up for the fact that we've essentially added another one of these when we multiply by 2, and we have to take off this sum of just the even terms. Okay, and so what we end up with then is that our f of x can be written as, this is 2, okay, so 2 times a geometric series. So this is the sum, n goes from 0 to infinity of 2 times x to the power n. That's this term right here. But then we have to subtract off this sum of a geometric series, but where the terms are all even. So this is the sum, n goes from 0 to infinity of x to the power 2n. Okay, these are both geometric series. You can plug in n values here and make sure that this is all the same. These are both geometric series, and so we know exactly how they behave. Okay, and since they're both geometric, we don't have to apply any ratio tests or anything like that. Again, we know exactly how they both behave. These both are absolutely convergent on the interval from -1 to 1, not including either endpoint. Okay, so there we go. So we've got our r equals 1 and our interval of convergence essentially for free. It's not totally for free because we had to rearrange it and make sure that we could write this as a sum or a difference of geometric series, but we can. And now, as I have talked through this, I've said everything correctly, but you should pause the video and make sure you understand it, okay? You cannot just subtract random series. They have to be absolutely convergent for you to subtract them and get a meaningful answer, or to even do this step up here where I did all this, okay? So this is all possible because our series is absolutely convergent on this interval. All right, and both of these are absolutely convergent on the same interval, and you should check that, okay, to make sure that you agree with that. Now, on to the next step. Once you're okay with all this, then the next step is to try to write a formula for this function that is not a power series formula. So, in other words, we want to use the fact that these are geometric series to write down their sums. And I'm sure you remember that the sum of the geometric series 2 times x to the n, this is equal to a over 1 minus r, right? The a is 2 and the r is x. So that's 2 over 1 minus x. And again, it's only defined on this interval, the same interval, right? On the other hand, this sum, n goes from 0 to infinity of x to the 2n, that can be thought of as the geometric series x squared to the power n. And so this one has a radius of 1. The geometric series is then 1 over 1 minus x squared. And all we have left to do is subtract these two to get our f of x, right? So f of x is then equal to 2 over 1 minus x minus 1 over 1 minus x squared. And we need a common denominator. We notice that 1 minus x times 1 plus x is exactly what we need. Then 2 plus 2x minus 1. So 2 plus 2x minus 1 all over 1 minus x squared, and that simplifies. 2 minus 1 is just 1. So this function is given by the function whose power series is this alternating 1, 2, 1, 2, and 2 coefficients. This is given by the function 1 plus 2x over 1 minus x squared, not everywhere, right? Only on this domain. So for negative 1 to x to 1. So x is strictly between negative 1 and 1.